Voilà, bonsoir à tous. Ça fait plaisir de revoir du monde à travers ces systèmes informatiques pour ce 18e séminaire Linux. Première édition en ligne, aussi une grande aventure pour nous, hein, on a un peu de préparation. Dans cette préparation-là, je tiens à remercier, avant de dérouler, Aksupchik, qui est à la régie. Je le vois là, il m'entend avaler son casque. Et puis, j'ai préparé quand même un peu de choses pour lui. C'est de coutume chez nous, hein. Un tout petit truc. Voilà. Une boîte de chocolat, comme ça, on pourra boire ça ou manger ça au café. Merci beaucoup, Jacques, hein, pour tout le travail. Déjà, en avance. Hein. Vu qu'on est en ligne, c'est difficile d'avoir tous les micros ouverts. On vous demandera de bien vouloir les fermer, hein, dans le mesure du possible. Par contre, on a les chats qui sont ouverts. Justement, Jacques, qui va s'occuper de ces chats. Sur ces chats-là, vous pouvez mettre les questions, puis on les prendra à la fin de chaque présentation s'il y a des choses à discuter. Hein, pas de souci. Et puis, on ouvrira aussi à la fin de chaque présentation pour ceux qui sont sur Jitsi. Ils pourront enclencher leur micro, que tout le monde entende, quoi. Hein, c'est peut-être ça la bonne solution. Voilà, je propose de regarder le programme. Alors, dans le programme, le welcome est fait. Dans le welcome, je dois excuser Jacques Genoul, le directeur de la HESS au Fribourg. Il m'a dit qu'il ne veut pas venir en ligne ce soir parce qu'il a d'autres obligations. On va présenter le CAS. On a une idée ici à l'école avec plusieurs professeurs de mettre en place un CAS dans le système embarqué. On va vous faire une petite présentation de ça. Puis surtout, on va ouvrir un questionnaire que vous aurez le plaisir de répondre après j'espère, le séminaire de ce soir, quoi. Et puis, je tiens ici à remercier Jonathan, déjà, Hendrix, de Rosas, du centre de compétences de Rosas, qui est un centre de compétences de l'école, ici de la HEIAFR, qui va nous présenter Little by Little from Model to System. Quelque chose certainement très passionnant, on va voir, hein, j'espère, je me réjouis. Et puis, à la fin, vers 6h moins quart, on aura les questions-réponses, hein, pour tout le monde. Voilà. Comme d'habitude, on a préparé un petit formulaire pour vous, pour le feedback. Vous avez ici le QR code, vous pouvez le scanner tout de suite si vous voulez, hein, pas de problème. Et puis, vous pouvez répondre à quelques questions qu'on a mises sur ce formulaire. C'est intéressant pour nous de savoir votre avis sur cette façon de faire. La première fois en ligne, c'est d'autant plus important si on doit changer quelque chose, si on peut garder, si on doit répéter ça. Enfin, je pense qu'on va être encore quelques temps confinés dans nos locaux. Donc, la possibilité ici de donner votre feedback et des propositions pour améliorer tout ça, quoi. Je propose qu'on passe à la présentation du CAS. Je vais aller chercher la présentation, voilà. Et puis, je dois partager, je pense, hein, Jacques. Je ne suis pas tout juste encore, hein. Voilà, je t'appelle. Et comme ça, voilà. C'est bon comme ça? On voit la présentation? Voilà, comme je vous ai dit en introduction, là, à l'école d'ingénieurs ici, on a l'envie de monter un CAS en système embarqué ou une série de CAS ou une série de modules en système embarqué. Ça vient de demandes qu'on a en interne, hein, des collaborateurs chez nous, mais on a aussi cette demande de quelques industriels. Le but est de faire la formation continue justement dans ce domaine et c'est de la proposer, comme marqué ici, la proposer au développement du monde industriel. C'est ça qu'on aimerait avoir. Ce n'est pas des managers, mais c'est des gens comme vous, hein, qui viennent pour améliorer, hein, ouvrir vos perspectives. On a regardé ce qui existait comme alternative sur le marché. Il y a relativement peu de choses. On voit il y a 3 CAS qui se donnent en Suisse allemande. Par contre, en Suisse romande, à notre connaissance, il y a juste la HE-ARC à Neuchâtel qui donne un CAS sur la sécurité embarquée. Quelle est l'offre qu'on proposerait de faire? C'est 3 sujets ou 3 domaines, 3 CAS. Un qui serait dans le Linux embarqué avec comme thème un module qui serait sur le développement, les environnements de développement des OS et des RTOS, la virtualisation, alors légère, lourde, hein, on va voir. Tout ce qui est update et deployment et sur des systèmes distribués. Ce serait un CAS avec ces modules-là. Un deuxième casque qu'on proposerait, c'est un casque sur l'IoT, avec une introduction sur les OS pour l'IoT, avec tout ce qui est protocole et la connectivité de ces IoT avec le cloud, avec tout ce qui est les stacks, les protocoles qui permettent de causer avec ces appareils. Naturellement, un sujet important, c'est le deployment des IoT, ça c'est important de le faire, et la gestion de flotte de devices chez les clients déployés. On a un troisième casque qu'on proposerait ici avec une série de modules aussi. C'est dans la sécurité et la safety. C'est un module ou un casque qui serait intéressant parce qu'on a justement avec Rosa un centre de compétences qui est hyper performant sur ce domaine-là. Donc, on proposerait de module-là, de la sécurité et la reliability au niveau système, la chose au niveau applicatif, la sécurité de l'IoT et puis tout ce qui est marketing, product industrialization. Ça, ce serait des trois casques qui sont suffisants pour les gens. On a aussi pensé d'avoir des modules qui seraient des modules de formation de base ou de mise à niveau pour certaines personnes. Typiquement, si on pense à des gens qui viendraient plutôt de l'électronique, qui voudraient aller dans le parti logiciel, qui pourraient améliorer dans les langages de programmation, dans la réseau peut-être. Il y a aussi des gens qui ont fait relativement peu de réseau. On voit aujourd'hui ces devices, ils sont tous connectés, donc il y a une partie réseau qui serait certainement intéressante. Il y a une partie de sécurité, de fiabilité, mais de base, qu'on pourrait offrir ici pour les gens. Aussi, sur les interfaces électroniques, savoir comment est-ce qu'on peut débugger les interfaces. Il y a Xbus qui sont là derrière, où c'est intéressant de pouvoir débugger. Il y a des modules plutôt pour la programmation FPGA. On a pensé à ça, on va arriver sur le marché, par exemple chez Xilinx. Ils ont des super FPGA avec des processeurs dessus, des Cortex A53, si je ne dis pas de bêtises, connectés avec une grosse FPGA. Donc, on pourrait faire du hardware software co-design là-dessus, quoi. C'est une série de modules. On a plus de détails, vous allez voir après dans un questionnaire qu'on vous demandera de bien vouloir remplir. Comment est-ce qu'on imaginait de mettre ces modules à disposition pour vous Donc, dans l'organisation, ces camps seraient faits sous forme de 4 modules. 4 modules qu'on a présentés juste avant, là-dedans. Il y en aurait 2 qui devraient être choisis dans le CAS, dans le thème du CAS, et puis 2 qui seraient à libre choix dans l'ensemble de l'offre qu'on a, quoi. Donc, on pourrait prendre 2 modules dans la partie Embedded Linux, et puis 2 dans le Core Modules, ou bien vous pouvez prendre 2 dans l'Embedded Linux, 1 dans l'IoT, 1 dans la sécurité, et puis là, vous aurez la possibilité d'avoir votre CAS en Embedded Linux. Pour un CAS, on a besoin, donc avec ces 4 modules, il faudrait faire 75 heures par module. On imagine de faire à peu près 50% en présentiel à l'école, avec 50% de ce temps-là de travail personnel à la maison. On a aussi pensé de faire ça sous forme de classe, en classe 8 fois à 3-4 périodes, une fois par semaine. L'idée de ça, c'est de pouvoir faire ça le soir, c'est-à-dire que les gens qui viendraient suivre ces modules n'aient pas l'obligation de devoir prendre congé pour les suivre. C'est ça, qu'on puisse travailler quand même. Et puis, on ajouterait à ces 8 périodes, à ces 8 leçons en classe, on ajouterait un samedi complet pour pouvoir faire un travail un peu plus approfondi là derrière. Dans le déroulement de ces cours, on pense faire 50% de théorie, puis environ 50% de pratique. Le côté pratique, je pense qu'il est important, spécialement pour les gens qui viennent du monde industriel, qui sont plus des étudiants qui ont l'habitude de rester assis une journée complète sur une chaise, quoi. Il y a toujours un problème de coût, naturellement, qui est lié à ça. Donc, on a regardé ce que ça coûterait pour nous pour faire un module. On demanderait quelque chose autour des 1500 francs pour suivre un module. Donc, pour les 8 journées à l'école plus le workshop. Et puis, pour les personnes qui voudraient suivre un CAS complet, ça coûterait 6 000 francs, quoi, à peu près. Ça, c'est une estimation des choses. Quelles sont les prochaines étapes qu'on a derrière? Donc, on a fait justement ce formulaire. Vous avez le lien ici. On le mettra encore, je pense, en Meetup, que vous puissiez accéder à ça directement. Et vous avez ce lien-là. Alors, le questionnaire, on est désolé, il est un tout petit peu long parce qu'on a demandé pour chacun des modules avec un petit peu de détails dedans. Ce que vous en pensez. Vous avez la possibilité, je peux peut-être cliquer, je ne sais pas si on le verra. On le voit. Jacques, si je clique, le formulaire, non? On voit le formulaire en ligne? Je pense.
On va cliquer dessus, oui, on va le voir.
On va le voir.
Non, on ne voit pas pour l'instant, on ne voit pas dans le
Alors, il faut peut-être que je fasse quelque chose. Je pense que je n'ai pas fait ça tout juste. Alors, je vais faire un truc. Voilà, partager. Et puis là, j'espère que je vais y arriver. Non, j'y arrive pas. Bref, c'est les aléas de ça. Vous pouvez cliquer sur ce lien-là chez vous, ou regarder ce lien-là, et puis vous aurez un joli formulaire avec pas mal de questions. On va l'envoyer aussi à nos experts en interne qu'on a pour les filières de informatique, télécommunications, respectivement de génie électrique, et envoyer à toutes les personnes qui sont susceptibles de participer à ça pour avoir votre réponse. Notre idée là derrière, dans ce formulaire-là, c'est de proposer des modules qui vous intéressent, vous. Hein. Ce n'est pas le choix des profs qu'on veut mettre là-dedans, mais c'est le besoin des développeurs dans le monde industriel, quoi. Après ce feedback, on vous demanderait de répondre ça jusqu'à la fin octobre. Donc, nous, après ça, on va analyser vos réponses. Et de ça, on va préparer un flyer, on espère, pour pouvoir le faire, si tout va bien, pour la fin novembre. On va ouvrir les inscriptions pour suivre ces modules, respectivement ces classes, en principe vers le début décembre. Et puis, notre idée, c'est de pouvoir débuter les premiers cours, hein, si tout va bien, en février, c'est-à-dire au semestre de printemps pour l'école ici en 2021. Alors, on verra en fonction de ce que les gens ont besoin. Hein. Si c'est un peu plus lourd, ce sera en automne, je pense. Mais l'idée, ce serait le printemps prochain pour partir avec la première série de cours. Voilà pour ma partie. Je vais donner la parole maintenant à Jonathan pour la présentation sur le Little by Little. Pardon?
Le petit laser.
Celui-là?
Ouais.
D'accord. Ici. Et puis, j'espère que ça marche. Tu le vois, Jacques? Cette présentation, cher. Je dois partager. Tu la vois? Non? Top sharing. Alors, je vais refaire une fois. Voilà. Partager. Rosace. Voilà. Comme ça. J'espère que c'est bon.
C'est bon.
Voilà. À toi, Jonathan.
Hop. Bonjour à tous. Alors, la présentation, je parle français, mais elle se fera en anglais. C'est un thème qui est beaucoup abordé, en fait, à Rosas. Donc, je vais switcher directement. So, my name is Jonathan Hendricks. I'm a safety engineer at Rosas Center here in Fribourg. We're a competence center of the school. I've worked about 2 years in model-based engineering, where we help industrials with models accomplish, in fact, some problems they're facing. And like that, we can achieve new solutions by applying research, in fact. So I'm going to talk about a few words about Rosas, and then I'm going to talk about MBE, model-based engineering. And then little by little, I'm going to take you through a model, and we're going to check how we can apply some simple stuff to a model and get little by little to the system. Then we're going to go beyond the model, and then we're going to have a small sum up. So, Rosas Center, like I said, Rosas, what does it stand for? Robust and Safe Systems. We're a competence center of the University of Applied Science and Arts here in Switzerland. We were established in June 2015, and we're about 26 collaborators. We support industrials, like I said, in different domains by applying applied research. We have safety, security, reliability, maintainability of systems, and digitalization. We work in automotive, aviation, cybersecurity, machinery, railway, you name it. They come with a problem, we apply research to it, and we try and find a solution. If we just look, we got services, where we got safety and reliability, like I was telling, cybersecurity, and then we got the domains, system engineering, where we apply services on demand. We got everything linked to digitalization, model-based engineering, digital twins. So we're trying to replicate a real system into a digital twin. And then we go operational engineering, so our digitalization. So you go real data feeding back into a model, and you can better engineer the next system you're trying to do. So now, why MBE? First of all, what is the common engineering process? Something we're facing a lot with the industrials. They come with a problem. Why? Because at the very start, they have a project meeting where they receive a specification, a document written that they're going to pass through electrical, software, sales guys, mechanical engineer. Everybody's going to pinpoint their little specification, and then they're going to try and do a first prototype, a second one, a third one, until they reach a final system. And this is project end. From the start to the finish, there's a lot of bottlenecks. The first one, prototyping, is costly. You're going to try maybe a first board, a second CPU, a third FPGA. So it's going to add to costs. Then from the first one to the end, it's going to take time, a lot of time. You have to redesign the board, redesign the software. You have to maybe make adjustments to mechanical pieces. You have to order prime material and so on and so forth. You can understand if there was a document passed through people, every time you pass that document, it's maybe going to change. And the first guy who passed through the document, he's not going to see the changes of the end. So the system, the specification are evolving, and not everybody is at the same page because it's every time changing. So there's a big collaboration problem. And finally, we saw this, costs, it's timely, there's a bad collaboration often. And you ask yourself, is it really what was needed at the end? Is my system really doing what I was wanting to do? What we intend to do, we try and bring MBE at the very beginning. What is MBE? Our goal or key objective is to reduce the development costs, but in fact, everything is a model. You don't have to buy anything. If you have to buy something, it's more prototypes because you want to try a specific thing on a specific processor, on a specific hardware. So we're going to lower the costs. We're going to lower also the risks because you try and model, in fact, the complexity in small pieces. So you're reducing the risk of doing a complex system. And finally, we talk about a single source of truth. So we're collaborating all together around a single model and not a document who is passed to each engineer. MBE, model-based engineering. This is our term. And in fact, we got three definitions. Model-based system engineering, the first one, the model-based safety assessment, and model-based design. If we look at the first one, what is model-based system engineering? System, we're going to define a system. You all know maybe the V cycle. So in fact, we're going to collaborate and define our system, unit design, software design, hardware, physical, integration, verification, validation, all using the model, in fact. We're going to iterate here, and we're going to try and validate higher level of requirements. Model-based safety assessment. You take your same system, a component, a small resistor has a failure mode, has three in fact, short circuit the entire loop on the entire system. How does the system react to such a failure? And this is exactly what's happening. We take model-based system engineering, model-based safety analysis, safety assessment, and we iterate on the V cycle. You can identify fault injection early in the model, trying something out, seeing how it reacts. If you have to add a little bit more security, a little bit more reliability on your system, you can know very early in the design phase. MBD, it would be stupid to talk about model-based engineering if we don't talk about digitization. We got smart sensors now. Use the smart data, feed it back into the model, and reiterate your design. You can have more information about aging, where are its problems, and the design phase of your system next time is going to increase in reliability, confidence in your system, because you injected exactly those values in it. So overall, we go model-based engineering englobes a lot of different aspects. Now, let's take a simple example. It's the phrase here. The customer wants an edge detection system which will be embedded on an autonomous vehicle. What does it mean? Let's break it up first. Edge detection, system, embedded, autonomous, and vehicle. 5 terms. First one, what we start is by understanding what we have to build. Edge detection, what does it mean? It means, in fact, I go some kind of an image and I want to see the borders. If we take the square here, you can see exactly the corners and everything. And you don't see what's inside of it. If it's smiling or not, you just see the borders. There's different algorithms, Sober, random forest, canny edge detection. Mathematically, if we take one of those, for example, the Sobel, we use matrices, approximation of the derivative, and then a gradient magnitude. If we take in images, might be simpler. You apply a filter on the X, a filter on the Y, results in here the derivatives, Then you apply the magnitude, the gradient magnitude, and then a threshold. There you go, simple. Remember these colors because they're going to be used again in the presentation. So this is edge detection. From the penguin, we define the edges of the penguin. Let's see how it goes if we use MATLAB. Have to go back to the pen, the arrow probably. Yes, there you go. MATLAB running, you can have simple functions, early simulations about what you have to do. Oop. Same thing for Python. You can use Python and you can do early simulations about the same thing. The coffee cup, we can see here the edges. So you can use, in fact, them to see and simulate already what you have to do. This is just the knowledge base. So then the edge detection, we know there's an edge detection algorithm. For example, Sobo, we just saw it. Now system. System, we have to capture an image and then do the algorithm and then maybe display it. So we can think about this as a block diagram. We've got a camera, a controller who will be having the algorithm, the filter, then the display. This can be done in PowerPoint, Visio, or anything else. Now you're going to tell to me, wait. A few seconds back, you said little by little from model to system. Where does the model come into account? If I go with this approach here, we'll come back exactly the same thing that Margaret Hamilton did for Apollo 11. This is the code, the paper stack code of the Apollo 11. What can you do with it? You can light a fire and that's more or less it. It's just going to stay there, get dust. You can't simulate it. You can't see which part of the code you can analyze it. You can't. It's just sitting there. This is today's engineering world, document-centric. We're having a paper thing containing everything and we're passing it on to people. What we intend to do and what we're trying to evolve to is to centralize everything around the model. The model, you can analyze it, optimize it. You can link real hardware to it, do different configurations, analysis about costs. Because if you take different sensors, you can see which one reacts better. So in fact, you can do also performance analysis. And you loop around this circle. This is what we call model-centric. Everything is about the model. For this, there's different languages. The one we're using is SysML, System Modeling Language. So let's take again our system. We want to do an edge detection unit. The first thing we're going to do, black box analysis. We're going to look, what is surrounding? How does it do? What does it have to react? Like the camera is filming me, it has to film the environment. So we link the environment to the edge detection unit. If we go further, what is the edge detection? Like we saw before, white box analysis, a camera, a controller, and then the display. We can even go further on, reiterate on the white box. And you can see the edge system becomes an algorithm where, if you remember, the X filter, the Y filter, the gradient, and the thresholds are modeled into your system. Architecture, system, we are good. Now if we go a little bit further on embedded autonomous, we can see here in Python and in MATLAB videos about exactly what we have to implement. The problem here is this was run on my big tower at work with a double display, a keyboard and a mouse, and I had to click to enable the function. So if we take the more keyword embedded, it's not really that. It has to be on an autonomous vehicle, so it has to be smaller. Smaller means maybe smaller computation power and longer time to evaluate the function. Also, the autonomous means self-aware system, so we have to be exactly more responsive than a human. Power consumption is also limited. So these aspects here come into account. The human response is 250 milliseconds, give or take. Then these two interact also on power consumption. So our system has to take that into account. But for the moment, we're just system level, but we already thought about it. If you take the vehicle now, the vehicle, where's safety? Safety related, it's going to be on the road with other vehicles, with motorcycles, bicycles. So there's a standard who has to be applied, ISO 26262 for road vehicles. About that, already the standards are putting forward semi-formal notation as SysML for safety requirements and software design. They're using those to, in fact, apply model-based development into systems. So now we encapsulate the customer requirement. We can go a little bit further. We can now take it down to the model. And here I'd just like to have a slide. This is very well a good work and
Est-ce que c'est bon?
C'est reparti.
c'est reparti.
Ok, alors on s'excuse pour ce désagrément. J'espère que c'est tout bon, que ça va continuer comme ça. Alors, Jonathan,
C'est tout bon, magnifique. Alors, d'après les slides, je dois remonter un petit poil, voilà, je crois par ici.
Je ne me rappelle plus vraiment où c'était, mais vas-y depuis ici.
Depuis ici. Ok, alors on va switch en anglais. So we identify customer requirements, every, in fact, little element in this requirement. So now if we go a little bit further, like I said, in fact, model, software, processor, hardware, this is exclusively the master's thesis of Frédéric Schenker, a colleague of mine, who worked on this on his thesis. And he evaluated, in fact, all the possibilities linked to bring from a model code generation the software, then embed it on this processor, and then integrate hardware, in fact, and see how all of this could be linked to model-based engineering. So, model in the loop. I was saying we're going to go from a model. So, in fact, you're going to run this model on your PC, on your tower. And in fact, you're not going to go on the hardware specifics. You're not going to be having the constraints about a processor, about a 32-bit, 64-bit. You're just going to run an algorithm who is the model. You're going to have the advantages that you're not limited by, in fact, any kind of hardware. If we take account the model, so the red box, the embedded system, is going to have the algorithm. If you look, we can do this in several different ways. MATLAB, if you're good at scripting, it's going to be writing code. So for some people, it's not a model. In fact, it could be understand like a model. Simulink is more blocks you're just trying to put together to achieve your function. So this is maybe more in the direction about model-based for a lot of people. But there's also Python, also scripting, also writing code a little bit. So if we take Simulink in MATLAB, you can already have two different aspects. You can have algorithm, or you can have different toolboxes who enable you to go on HDL. So you're targeting already a specific hardware you're going to use. HDL, hardware design language, description language, sorry. So if we take now the algorithm part, you can see very simple. In Simulink, you just take blocks. A 2D FER filter, you apply the matrices we saw, and then you get your function. If you remember again the colors, X filter, Y, gradient, thresholds. Simple. This is exactly the Sobel filter. If we go in the HDL part, same. X filter, gradient, thresholds. However, other different blocks. The FPGA guys in the online seminar, you can see here there's delays block. Those delays, you know well, you have to synchronize, in fact, all your signals. And these are there exactly for that. You've got stages, in fact, and this is going to introduce, in fact, a little bit more specific to your model. Like, for instance, this box here, it's exactly, in fact, retrieving pixel per pixel for an image. So you're not passing the entire image, you're passing it here, but then you're going to have different aspects just to get it, in fact, the pixel you want. Is the signal still there? Yeah. Okay, now if we look HDL and algorithm, you go a penguin, and then you get the image. Exactly the same. The model is not limited by the hardware you're having. It's exactly, in fact, the same representation, and you're going to have the same results. So model-wise, we're good for the edge detection system. We can go now to software or processor. Software. From the model, we're going to go to software. How do we do the link? The link is by code generation. A lot of people say code generation, we're not sure about it. We're not sure how we can make confidence about it. MATLAB implements a good code generation. Why a good one? Because in fact, if you look after what the standard asks, they have to say, okay, your compiler has to be certified. It has to follow different rules. For example, one is MISRA-C 2012. It contains 143 rules that have to be applied to code for road vehicles. So you have to meet those 143 rules to be able to say your software is okay. So if you're a good coder and you know those rules, go ahead. But other than that, code generation is well accepted by certification authorities. So now if we look, we go mill, sil, pill. Mill, we covered it just before. Remember, Symmetric model executed on a host PC, no hardware, not linked to any specific hardware. If we look at sil, software in the loop, it's generated software code, C language, and it's gonna be executed this time on the PC. So you're targeting, in fact, this time a processor for certain C code. If we look, the principle is now having the constraints of the code. So memory allocation, cache, constraints on the size you're going to be using, and so on and so forth. Pill, processor in the loop, generated software code for here a specific processor. In this case, it's going to be an ARM processor. We're going to be using the BeagleBone Black. An additional code for, in fact, interfacing this small processor. Like I said, the processor this time, processor in the loop, you're going to put a small processor in your model, run it together, and see the results. You're going to have the constraints of this time again, the software, register, cache, and also like that, but also the running performance of your processor. Like I said, we're going to be using the BeagleBone plan, and there's a USB link, TCP/IP, between each of them. Like that, we can communicate back the results to the target PC. If we look at how it implements, we run simulation. It takes its time. Why is that? Because you have to communicate back and forth to the BeagleBone. But other than that, the mail aspects arrives, the sil, and the pill. These two images here are comparison. You compare, in fact, the sil was the mill and the pill was the mill. You can see they're exactly black because there's no difference, actually. We can see in the next slide now, I'm going to run again some code, but this time I'm going to change, in fact, a small aspect, the thresholds. I'm going to change it to 50 to 100. So it means the mill is going to behave differently from the sil and pill, because before we generated from the mill. And now you're going to see the mill comes up, the sil and the pill. And you see here the differences, in fact, in the two of them. We can change it again, make it to a 200, for example, and rerun the simulation again. Here, you see, you're seeing much less. You put the threshold so high that there's a lot of differences, and you can see those differences coming back up here. So with this, what do? We went from model, code generated in software, and then for a particular processor. Mill, sil, pill. If we talk now about a little bit of performance, sil, 95 milliseconds, targeted on a host PC with an Intel Xeon 3.5 gigahertz. If we take the pill processor, 9 seconds for a single image. Not kind of autonomous yet. Why is that? The first thing you could say, okay, you have profiling on the additional software you're putting on the processor, so it has a little bit more job to do. You got small flags that are being triggered, information being saved, and so on and so forth. So that additional codes gives a little bit bigger software that has to be generated and executed. So the load here is mostly that. Second thing is also the Cortex is at 32-bit. So maybe your model is using doubles, you're using 64-bit. If you change your model, you can maybe bring it a little bit down. Indeed, from 9 seconds, we go back to 1 second now. We're tilting a little bit the model, but still generating sil, pill, and executing. You could also ask yourself, okay, do I have to have 4K image? No, you can maybe go down to a 480 pixel. That could be okay. It's a trade-off between the system requirements and now what you're trying to implement. If we look now at hardware-wise, hardware is what you're going to take exactly your hardware, the camera and everything, and try and see how everything reacts. So if we look here, it's exactly the same model. You remember those filters, X, Y, gradient, thresholds. The only thing more is, in fact, MATLAB enables us to put a camera in the model. So we're going to have a model of this, we're going to do software, and then we're going to do processor. We're going to put down the processor, so the processor is capable of, in fact, getting the images from the camera. What does it give? You can see it's not a 30 frame per second. So still, if we go on autonomous vehicle, on parole, we're probably going to hit a lot of people if we take this camera on autonomous vehicle. You can see here a nice effect. This is the camera looking into its own image. So camera inception, if you want such. So BeagleBone, maybe we have to readapt the model, have it faster. If we take maybe a more powerful, like the Odori XU4, already there, you can see the images are way faster. The processing is going way faster. So is this the better solution? For maybe the BeagleBone, we were at 50 francs. The Odroid were at 70, and we got more power. This could also be a solution. If we look, pretty smooth, and you can see people passing and stuff like that. So for autonomous driving, it could be a solution. There's still a lot of optimization you can bring to your model to, in fact, have it better tailored for your final application. You can also think about, okay, we have those toolbox about HDO. Maybe you can integrate FPGAs in the process and have it, in fact, do way better and go up to 60 frames per second. Who knows? These are things you can go step by step into the model. For example, here, what do we buy? A BeagleBone Blam Odroid XU4. So the cost, more give or take, maximum 200 francs. Now, if we go just a little bit beyond this, it's a simple example, yes. Now think about industrial. Industrial, they're doing big systems. We're at Rosas doing safety, in fact. Safety, often they arrive with a system already done, and they're trying to perform analysis on them. So we're trying to see where we can come into. Often, a big problem is they have an idea and they have different systems for exactly the same idea. A sensor can be changed at a different place on that engine, and in fact give different performance, different information to exactly the same processor. Configuration is a big issue this time. So with the model, you can have exactly the same, and in fact the camera can be a different camera in this example here. The embedded system, like we just showed, it can be a BeagleBone Black, it can be a Raspberry, it can be a Odroid. It could also be, in fact, like I said, embedded systems and FPGA. All of these you can change, and you can also add redundancy. See how maybe a dual, triple channel is going to go up. Have information about weight, prices, and so on. If you add those parameters into your model, it's becoming not just something to simulate, but it's becoming a working tool. I was talking about safety. As you saw before, there was MBSA, fault injection. Fault injection is critical these days. We have to simulate in very complex systems injection of faults to show, in fact, that our system reacts to such events. What happens nowadays, you got those on airplanes where they have to do a blade crash into the actual engine. It's mandatory to do it hardware, but not often you want to do that because it's going to break your engine, your hardware. A model is not going to break. It's just going to maybe crash. If it crashes, it's on your host computer. It's not in the air. It's not flying. It's safe. It's on your computer. And fault injection with models is a great way in proving, in fact, that you can go further in safety. Like I said, MBE, we go design, safety, system. There's a lot of different applications behind the models. It's just of where and how you can think about it and apply it to your problems. Now, to finish up, I'm not gonna lie, there are a lot of challenges if you want to move to model-based. It's a new business case. It's unknown at first because you have no idea where is the return on investments. Industrialization-wise, you have to take step by step to arrive at an industrial solution. It's new processes, new approach, probably a new tool, new methodology. All of this you have to recycle. It's a lot of things. The only thing I can tell you, and for sure we applied it on different projects, is that very early, in fact, in your recycle, you can validate your system with your system requirements. You lower your cost, lower your risks, collaborate all together. Second thing is, it's applicable to a lot of different domains. If you add digitalization, if you add real world data into your model, you can better engineer, better see where something crashed. Overall, it's a good methodology, but it's going to take time to implement in industrials. Thank you very much. This was my talk. And if you have any more questions about model-based, please feel free to contact us or any of my team about aspects on safety, model-based and reliability, system engineering, and so on. Thank you.
Merci, Jonathan. Je ne sais pas s'il y a des questions.
Alors pour l'instant, j'ai aucune question qui sont arrivées sur YouTube, ni sur Jitsi. Si vous avez des questions, n'hésitez pas à les écrire soit dans le live chat de YouTube, soit à les poser en live sur Jitsi.
Vous pouvez prendre la parole aussi si vous voulez. Pas de questions? Donc, s'il n'y a pas de questions, je tiens à remercier Jonathan pour sa présentation. Votre travail, je pense qu'il y a des tas de choses ici intéressantes à apprendre, à profiter pour l'industriel. Et puis, pour sa présentation, comme toujours, une petite bouteille, voilà, et une boîte de chocolat. Merci beaucoup, Jonathan. Toujours pas de questions? Non? Rien? Donc, on vous remercie tous d'avoir participé à cette première session. On va regarder vos feedbacks avec beaucoup d'attention pour voir ce qu'on peut améliorer. Et puis, on va essayer de refaire une session avant qu'on puisse se revoir en présentiel, je pense. On va voir comment ça se passe chez nous, si on a des sujets qui sont intéressants. Aussi, proposer des sujets qu'on puisse les aborder dans ces séminaires. Et puis, j'espère qu'on se voit ce printemps en présentiel. On verra si la Confédération nous laisse faire ça et si l'école nous laisse faire ça. Sinon, à tous, une excellente soirée. Merci beaucoup. Et puis, à la prochaine. Bonne soirée.
Merci beaucoup.